Okay, folks, so I'm going to give you a presentation that I gave in 2019 for the Kentucky Lake section of the American Chemical Society. So my talk today is on the chemistry of whiskey. I'm not going to say I'm an expert, but I'm definitely what you'd call a connoisseur. I do enjoy a good whiskey now and then. So it's something that I've really taken interest to. So I did some research, collected a bunch of articles, and put together this nice little presentation to talk about the chemistry of whiskey. So this was actually based on the KLS's Chemistry of series. They talked about the chemistry of like various different things, such as like how paper is made and produced, the chemistry of beer. This is a slide that was used on the chemistry of beer talk that was given in Paducah, like say about the year before. For beer, you needed 4 big ingredients. You need water, you need the wheat, you need the yeast, and you needed the hops. All those 3 things were needed for beer. Well, whiskey is a little different in that you don't need hops at all. Hops are there to help, it's like kind of sterilize the beer so that it can last for longer periods of time. But this is true for all whiskey. We do not need, the alcohol content is high enough that we do not need the hops at all to keep it sterile. And this is true of actually most spirits in general. No hops. In fact, we don't need wheat. We can use just about any starch or sugar source as our feedstock. We have corn, we have barley, we have sugarcane, we have, what is that? Oh, the one they use in agave. Well, yeah, agave, I'm pretty sure. You can use potatoes. You can just use sugar. Any source of sugar can be made into spirits. You can use beets. You can use radishes. Anything that has complex carbohydrates can be made into a spirit. And if anything, spirits are more focused on the technique and the instrumentation used than just the ingredients. Some people will mix in various different fruits or whatever to give the beer a certain flavor, but it's not just the fermentation process where everything happens. With whiskey and spirits in general, you have to distill, and depending on whether you use like a pot still or various different column distillations and multiple distillations, you can have different flavor profiles. Whether you use charcoal or some sort of filtration system to remove some of the negative flavors, that's also done. You can use barrels of various woods and varieties to then imbue and age them. This is a lot more chemistry than just simple biology like it is in beer. So all these things help to develop a final product that is unique compared to the original starting ingredients. That all these, you can take the same starting materials, ferment them the same way, but by applying different techniques to them, have an entirely different radical product. These will change the flavor profiles, even will be mainly used to increase the alcohol by volume content, or ABV. Distillation will help get that up. Now, this chart is just a simple way to distinguish the various spirits together, just different ways to look at them. All the spirits are on the right. I mean, not all the spirits, but a good deal of them. And you see, they've distinguished them whether they use no barrels to age them, so that's not aged, They use new fresh barrels to age them, or yellow used barrels to age them. Whether they use a pot still, uh, and then a column still, just a column still, column or pot, or they're blended various whiskeys together. Then it further breaks down into what grains. Does it matter what grain? Is it have to be barley? Is it malt barley? Is it wheat? Is it malted wheat? Rye, malted rye, corn? Is it fruit-based liqueur, which is used in various fortified wines and brandy? It's like grapes, grape must, apples, and other fruit. Or is it sugarcane and molasses or agave, things like tequilas and rum? Then what other things is done to it? Is it smoked, for example? Is it flavored? Is it filtered? Are botanicals added? Botanicals very important in things like gin and liqueurs. So if you've it's sugar added, it's wine added, and also then what country does it come from? Even then, because Irish whiskey traditionally has to come from Ireland. Scotch has to come from Scotland. Canadian whiskey, Canada. Mexico is usually the purchaser of mezcal and tequila. Jamaica is for the true rum. Spain makes the true sherry. So all these kind of little distinctions can then further change how we talk about this. So, kind of take a minute to look at this, but it's rather nice in a way. Now we need to look at just how whiskey is made, the simple techniques before we dive into the heavy chemistry here. The first thing is we need to do is the mashing. Now, when we mash, you take some ground corn, some rye, or some malted barley, mix it with some clean, fresh spring water, and that becomes what's called the mash. This is going to break down some of the complicated sugars into simpler sugars. The process of malting even comes before this. Like if you're having a malted barley, what's happening is you allow the seeds to partially germinate and then you kiln dry it. So you use a hot furnace to essentially halt the germination. This germination allows for a partial breakdown of the starches and is the first occurrence of the Maillard reaction, which we'll talk more about a little bit later. But this mashing is what's going to break down the sugars to make the yeast. We're going to have amylose and amylopectin, which is the amylose is the long chain sugar and straight. And the amylopectin is the branched sugars, can be broken down into simple sugars like maltoses and dextroses. And even in the simplest steps where you mix these sugars together with the spring water, every part is important. The spring water source is highly important. You have contaminants there, it's going to be contaminants later. So people like Jack Daniels and Dickel, two Tennessee distilleries, use fresh spring water out of limestone deposits. The limestone prevents iron and gives it a very high calcium source, which in turn is a good feedstock for the yeast. Now, what I forgot to mention here is that sometimes when you have a whiskey, it's labeled as sour mash. What the sour mash is when they add the fresh corn, rye, or malted barley, sometimes they add in a little bit of the leftover solution from the previous one, and thus creating you have some already partially dissolved sugars, you have some of the yeast already ready, and the high acid content there helps flavor this, and thus it's called sour mash. Sour because of the acid. In the fermentation step, we add yeast, we add the sugar, and just time. We try to watch out to prevent too much oxygen getting in there. And what we have is ethanol and a lot of CO2 it producing. Now, so we want this in anaerobic conditions, so essentially as much without oxygen as possible. These aerobic conditions will be the chief source of what we call congeners. The congeners here are all the little side products that are oftentimes responsible for good flavoring and a lot of the bad flavoring. And sometimes these congeners are what yields our headaches when we get a hangover. Congeners like aldehydes, the acids, the esters, fusel oils, all these are, at this step, we want as little of these as possible. Later on, we'll see, oh, it's actually kind of important. But right now, no, we don't want any congeners. So things like, of course, calcium, like from our water source, or dead yeast from our sour mash, will provide plenty of nutrients to help our yeast grow. However, these first two steps, you suffer the highest risk of bacterial infection, which will then spoil this. Because bacterial infection produces a large amount of lactic acid, acetic acid, and butyric acid. And they'll make your alcohol taste all off. We do not want fully oxidized alcohols. We don't want to convert them into acids. Of course, iron-rich water, I was saying, should be avoided at all costs because it turns the yeast black and will eventually affect the flavor of the end product. So keeping those free from there makes the best alcohol. Now, distillation, that's where we really know this well. You could have a pot still like you see on the left, where it's just a simple still where you heat up and it's going to come out the flute. But you could also have various different column stills. All these will be used to create a very complex spirit. Sometimes we'll use multiple distillations to get this. Well, the first thing we're going to do is to separate and concentrate the alcohol in the first step. So I'll remove the alcohol and the congeners from the majority of the just water. The first distillation usually covers that. But the second distillation is where we're going to separate what's called the hearts from the heads and the tails. The heads are the low carbon chains, such as methanol, that can lead to blindness. So the low carbon chains means they boil more quickly, thus come off first, head first, if you will. The tails are the heavier carbon chains that can cause headaches and among other things. These are fusel oils. We want to separate them so we get the, as pure as we can, hearts. Now, the column distillation we see in the middle and on the right, you can create various different heights, but each of those little circles represents a little stopping point. We have these little plates like you see there where the liquid can condense and fall back down. And so it really becomes a very effective way of separating a complex molecule based on its boiling point. The pot still is a little bit more crude, but it keeps more of the flavor profiles in there. The column distillation is very useful for producing a light, crisper spirit. We use this to make vodka and other liqueurs. Vodka is actually supposed to be as pure alcohol as you can with very little congeners. So it doesn't really matter that we're making this from potatoes. Potatoes aren't really meant to have a lot of byproducts. We're going to purify this. A vodka is often bragged about by how many times it's distilled, because you're essentially, how pure is the product? You don't want a bunch of extra stuff in it. you want it as just as pure alcohol as you can. When we usually talk about the distillation, it almost always occurs in copper pots. And why is that? The reason that copper is still the metal of choice is because, one, it's malleable, so we can hammer it into shape very easily. Two, it's very long lasting. So if you take care of it right, your pot will last for a very, very long time. And three, it has a very high thermal capacity, so meaning it's very easy to heat up. And four, probably one of the most useful ones is its antimicrobial and antiviral properties, that it can kill microbes beyond just the boiling effect. And five, it will reacts with sulfur compounds to remove that from the spirit. We don't want skunky beer. We want to remove the sulfur from there, and it's going to react with the copper and form on the side, which we will have to refresh, but it's better to remove it there than have to remove it later. And it will catalyze the Maillard reaction, which we'll once again talk about in just a second. And the last reason is it's very resistant to corrosion, even at its high temperature and humidity that we're going to need it at. So it's much better than, say, stainless steel, even though stainless steel is probably a bit cheaper because of all these little benefits. So the distillation is supposed to concentrate my alcohol and remove a lot of these congeners. But one of the side benefits of this distillation is the formation of the Maillard reaction. The Maillard reaction is as follows. You see, we have some simple amines that will react with our straight chain sugars. When our sugars uncyclize, when they split open, they can then react. They form aldehydes at one end and alcohols at all the other carbons. And these essentially, the Maillard replaces the terminal with the aldehyde with a amine. And this amine can then result in a formation of a ketoamine. Now, while this reaction is not just limited to alcohol, where we've probably more likely seen this in our everyday lives is anytime you're baking. Anytime you have sugars and proteins, and you're allowing these amino acids to mix under heat, you're going to form the Maillard reaction. You form a variety of aldehydes, pyrules, furans, resulting in caramel flavoring, roasted flavoring, and various nutty flavors that we can enjoy. Examples of Maillard products are pyazines, which are 6-membered rings with 2 nitrogens in them. Pyrules, 5-membered 1 nitrogen rings. Alkyl and acyl pyridines, which are 6-membered 1 nitrogen rings. Furans and furanones, which are versions of 5-member rings with oxygen within it. Oxazoles, the 5-member rings that containing both oxygen and nitrogen. And thiophenes, 5-member rings with sulfurs in them. Now, once we've distilled this and we've removed any sulfur that's reacted with the copper, how do we clean out the copper still? Well, you can clean it out simply by running with either a vinegar wash or a powdered brewery wash buffered alkali solution, which is essentially washing soda, which is sodium carbonate, and a sodium silicate. So we can wash that and it'll react the sulfur and refresh your copper still, so it's good as new. Now, this step is not used for every whiskey, but this is used locally in both Jack Daniel's distillery and in Dickel distillery. It's the mellowing process also referred to the Lincoln County process from where it was developed. It's used to help make a better whiskey right away. If you're not going to age the whiskey for a long period of time, this helps remove a lot of the congeners that can give whiskey their distinct, sometimes unpleasant taste. So the main thing they have to do is they take sugar maple trees and turn it into charcoal. As we all hopefully know, charcoal filters out a lot of impurities. If you've ever been poisoned, they might tell you to suck on a charcoal briquette and that it absorbs some of the things. We use these for various ways to absorb metals and other things, other impurities, various different sources. That charcoal is ideal for this. So we filtered the distilled whiskey through this charcoal filter, and this will remove a lot of the congeners, resulting in a much mellower whiskey. Now, if you compare Tennessee sipping whiskey to Kentucky bourbon, you have a very different type. Now, Jack Daniels and Dickel use this method, both, as I mentioned, they use their own little slightly different method each time. In fact, if you've ever had Gentleman Jack is filtered a second time after aging, but prior to bottling. Though you must take a lot of care not to mellow it too much, or else it will filter out all of the congeners and thus go back to a clear spirit again. You do not want a clear spirit unless you're going for vodka. But so Gentleman Jack is you filter it, you let it age somewhat, and then they filter just a pinch just to remove some of the congeners. So you want mellow. And of course, to make this charcoal, they have to burn some maple down, but they don't want to add any accelerant. Well, at least any accelerant that could add any impurity. So what they actually do is they add, at least at Dickel, they add some whiskey as their accelerant. So any byproducts are only coming from the whiskey itself and not from any other fuel source. Maturation is arguably the most important step for any type of whiskey or spirit, in that what changes a simple spirit like moonshine, white lightning to some, to whiskey. I mean, essentially what you're doing is you're changing the entire flavor profile. Every whiskey or any sort of spirit comes off the still clear to the naked eye. It's only when we age it that it develops any sort of coloring at all. In fact, some states have legally defined a whiskey as a liquor that requires a minimum aging time before it can be called a whiskey. It needs like at least 2 years in a barrel before it can be called a whiskey. So some people, they do the bare minimum. Some people go for 5, 10, 15 years. But the result is you have a couple different effects. You directly add wood extractives. You allow reactions to occur between the congeners that were present and these wood extractives. You allow reactions between the wood extractives themselves, and you allow some of the more volatile congeners to evaporate off. And as you see in the new whiskey A, B, C, and D, it gets a more amber color as it allowed to age longer and longer. I mean, in American whiskeys, we typically use new charred or toasted oak barrels to age the spirit. Though in some countries, such as Ireland and Scotland, they will age their whiskeys in used barrels, sometimes swapping with the makers of various wines and fortified wines to imbue unique flavors. Like you might use a sherry cask, something that's been like, we stored a bunch of sherry in this, and they'll trade their whiskey barrels with the sherry company, and thus each guy gets their own benefits. In fact, I've had some of Dickel's Tabasco whiskey where they have exchanged Tabasco barrels with the Tabasco company, and essentially you get a little spicier whiskey. And of course, now the Tabasco then gets a little bit of more whiskey flavoring to it. So they each get their own benefits and they help each other out. Now, it's not always matured in the same barrel. Sometimes we mature it in one barrel for a couple years and we change it to another to get different flavor profiles. But things like the wood type, how much the wood is charred or toasted, how many times the barrel has been used, and even the conditions the barrel is stored under will all contribute to the types and quantities of extractives that can be present. Now, technically, according to my one source, there's 11 key analytics for judging the degree of maturation. One is the proof, which is alcohol by volume. Two, it's a total acidity, measured in grams of acetic acid per 100 liters. The fixed acidity, which is the total acidity minus the volatile acidity. So what volatile, subtracting out the volatile acids. The esters, how many esters you have, grams of ester acetate per 100 mils. Aldehydes, measured as grams as acetaldehyde. The furfurols, the fusel oils, measured as amyl alcohol. Solids, like how much solids float in there. Color, what is its absorption? So how amber does it appear? The tannin content, measured as tannic acid, and finally the pH. This is a scientific way to quantify the qualities of a liquor, but you really need a refined palate to taste and say, is this good? You can't just read off the chemistry of this and say, is this good? Will you enjoy this? Will it sell? You need a tongue to really tell that. So the last step is enjoying it. I mean, after maturation from it could be years, could be just mere days, whatever is legally defined, and they want to do it. Some of these guys are blended. A lot of these have to be blended by master distillers for consistency. You don't want, unless you're dealing with small batch, you don't want your Jack Daniels to taste one way one week and one way another week. You want them all to taste essentially the same. You don't want to be like, oh, that was a really good barrel, and you buy the next one and you're like, oh, what the heck happened? So even barrel to barrel, you don't want to like, oh, this one worked well, this one works. So you have master distillers tasting and mixing from barrel to barrel so that overall the entire batch tastes the same. Small batch, they're allowed for some degree of differentiation because that's what you're going for. That's what you're paying for in a small batch. At this point, it must be proofed for alcohol content. It typically is going to be carefully diluted to get its set alcohol by volume before it's bottled. Now, sometimes they'll give you cask strength, so it'd be undiluted, be a little bit stronger, a little bit more powerful. But most of the time, they are going to dilute this. And they're not really, they have to be very careful. They don't want to add too much water at once and thus cause a lot of the congeners to crash out. They want to slowly add this so the whiskey can mix in and dilute gradually. Now, but ideally, the alcohol content of a proofed it should be proofed through the whole process, with its distillation to a max of 160 proof, aged to no more than 125 proof, and then bottled at least 80 proof on most whiskeys. Whiskey is arguably best enjoyed either neat, which means without any additives, or with just a small amount of water. This small amount of water is there is because it's going to change how the congeners like volatilize, and it's going to cause them to kind of quickly evaporate, and it changes the flavor profile and the aromatic profile, so you can reaches your nose quicker and thus changing the flavor just a bit. It's very arguable what is the best proof to put in the bottle, as the solution properties will actually vary with its proofage. So there's a very good reason why most whiskeys and liquors are either between 80 proof or 110 proof or some combination of there. That while ethanol and water are supposedly miscible in all mole fractions, the solvent properties change drastically depending on the mole fraction. Ethanol achieves a maximum solvation shell of 5.3 water molecules per ethanol that are largely present in our 40% alcohol by volume or 80 proof. In fact, Mendeleev, as the periodic table Mendeleev, did some viscosity studies on alcohol to try to figure out what is the best type of liquors. He found out that alcohol achieved a maximum viscosity at 47% alcohol by volume. And so some people argue, well, you want the maximum amount of, you don't want excess water, or you want the maximum amount of solvated ethanol, so maybe you want 80 proof. But if you want a very viscous mouthfeel, maybe you want 90 proof. Yet even noted that due to the nature of the cage-like structure in water with hydrogen bonding, that when mixed with alcohol, the volume is not directly additive. This is a concept in physical chemistry, in that the volume of mixing, when you add 1 ml of water to 1 ml of ethanol, you'd expect to have 2 mils. But because of the cage-like nature, you don't always get a 1-to-1 ratio. Maybe you get 1.9 mils, 1.8, and so you get a change in the change in the volume of mixing on this. So ethanol can actually fit on the tail of a molecule within the cage to produce a contraction in volume. The largest contraction occurs at 1 ethanol to 3 waters, which is close to 110 alcohol by volume. So your argument here is, what type of properties do you want? So a solvent system will affect congener solubility and how much reactions you have. Slow dilution is necessary when we go from the cask strength to the bottle strength, because any drastic changes, though, will result in saponification of the esters. If we add water too quickly, we're going to break down our beautiful flavor profile esters back into essentially a soapy flavor. We're going to break them apart again, and we do not want that. We want to avoid that at all costs. So slow dilution will then will prevent that from happening. So the question comes, and one last thing, looking at to dilute or not to dilute. Should you drink your alcohol neat or with water? What is actually going on? So alcohol and water are not an ideal homogeneous mixture. Many of the volatile flavor congeners are largely soluble in the ethanol only. So this is a kind of a picture of the ethanol and water. You see that the ethanol molecule, the ones with the blue on it, are largely concentrated on both sides of this mixture, that they essentially form on the, they do dissolve into the water, but they largely, it's more heterogeneous mixture where the ethanol favors the top and bottom. So the congeners, which are largely soluble in the ethanol, are largely in the top and the bottom. Addition of the water that decreases the ethanol solvation shell, and thus increasing the volatility. And so when we add a little bit of water to the whiskey, the congeners kind of like vaporize, and they change how your nose detects them and how your mouth tastes them. That's changing the flavor profile. Of course, even when starting water source is very important, the minerals there and the pH there of your starting water source will change the flavor and mouthfeel. The drink texture and flavor durations and intensities can be adjusted just by changing the water you use to distill or dilute your spirit. Some bottlers will swear by using rainwater as the best water type when you bottle this, just because it has the right cation and anions doing that. But there is a study where they looked at the water source when producing gin, using a distillation and dilution step. They used France spring mineral water, they used German spring mineral water, Fiji water, Icelandic volcanic glacial mineral water, England recycled domestic water, and England demineralized domestic water. And they were able to like pretty much distinguish between a lot of these. That but by looking at the mineral content of these, you could tell one of these was superior. I can't remember right off the bat, but which one was preferred. But the idea is that they did not all taste the same based on their water sources. Now, what goes into maturation? How does maturation really work? So this is special. What makes what's whiskey and other aged spirits special to, say, White Lightning or moonshine? That's what makes this so different. So the irony in aging is that the oak barrels put in a lot of the same congeners that distillation has just taken out. But these barrels are going to put them in gradually and allow for a lot of other reactions to happen. These barrels will typically be stored in a warehouse and allowed to be experience weather conditions, different humidities going up and down. They're not going to be in a room that's the same temperature all throughout. They're going to experience different humidities, different heat waves, and it's going to result in various things. So first, when you toast the barrels, you cause a partial decomposition of the lignin within the barrels and the cellulose and hemicellulose. So lignin is this is just a small fragment of lignin. It's a very, very complicated alcohol aromatic ring system that it's really complex and really hard to deal with. And it breaks this partially down upon burning this. It's going to increase the surface area, and because it's going to make much more porous surface. And it's going to release acetic acids and methanols into the alcohol upon toasting. So as the barrels undergo these series of hot and cold seasonal things and hot and cold diurnal cycles, it's going to result in the gasification of ethanol and other congeners. And the basic idea is that there's a mixture of Henry's law and the ideal gas law, that as the temperature goes up and essentially the whiskey will move into the pores and then move out of the pores, move into the barrel, out of the barrel, and slowly dissolve little bits of that barrel into that whiskey, little bits of those congeners into the whiskey. Higher temperature, further expansion into the wood, greater solubility of the wood and sugars and phenylaldehydes, faster reactions. Then it cools down and it contracts. Now, as time passes, these solvents and the other volatiles will slowly evaporate from the barrel, resulting in a loss that's often called the angel's share. That I believe angels coming into the storeroom, taking a little sip, and that's just something, a price that the distillers had to pay to make the best thing. And this would, you're worried about, oh, we're releasing methanol back into the air, but hey, the methanol will evaporate and it makes it fine. And this will help concentrate the flavors. This angel's share. So at a certain period of aging, you're not going to really have any more reactions. All you're going to do is concentrate those flavors. Now, The majority of these complex congeners come from the degradation of lignin. Toasting the barrels will serve to initially speed up this decomposition of lignin, but further decomposition will occur over time, over the whole life of the barrel. And if used barrels would actually contribute a much lower concentration of the following compounds, is that they've already given a large concentration the first time around. So it produces a different flavor profile because you're getting less of these guys. But so some of these guys like aldehydes and like furfural and syringaldehyde are very quick to dissolve into the barrel or from the barrel, like the almond-like grainy aroma and a spicy woody aroma, these furfurols and the syringaldehyde. You get some aromatic alcohols like vanillin and guaiacol and its various derivatives. They're much slower to dissolve. They take longer than 90 days to dissolve, resulting in vanilla flavoring and smoky flavorings. So if you only age it for very quick, you're going to get these only the syringaldehydes and furfurols. You're not going to get the smoky flavoring. Now, while we didn't want these acid byproducts right off the bat when we talked about fermentation, these acids are desired during the maturation phase because you're going to want acids because as a catalyst for some of the reactions we're going to do. So we have like things like acetic acid, vinegar, glucuronic acid, as you see there, gallic acid, syringic acid, just like syringaldehyde, vanillic acid, just like vanillin, p-coumaric acid, and ferulic acid. Now, acetic acid is the most abundant, perhaps the most important for its contributions. But this is only a small portion of the acids that can form. But these acids were formed just during the oxidation of lignin. Just lignin gets partially oxidized when it's burned, and so easily break off. These acids will eventually lower the pH of the spirit and catalyze some of the reactions. They need a low pH, so you need a proton donors to do that. And these guys are going to be providing just that effect. And of course, we have tannins. Tannin byproducts are just very complex, essentially lignins. They're like larger portions of the lignin that still remained intact. Tannins are often present in wines and ciders. All these extractives contain highly reacted functional groups. And in addition to these extractives, you often get ash and various metals that can be extracted from the wood. But so these are elagitannins are hydrolyzable, meaning that they can be split by water to produce acids and sugars upon cleavage. They can also allow for oxidative polymerization, all these resulting in various flavor changes. Like we can get these wood extractives now that they've gone into the whiskey, can start reacting both with the starting liqueurs and the congeners there and other wood extractives that have just dissolved. They undergo a variety of different reactions like hydrolytic reactions, where hydrolytic means cleaving with water. So we're breaking bonds apart with water, which is going to be all from there. Oxidation. Oxidation reactions is the loss of electrons resulting in greater amounts of carbon oxygen bonds. Esterification, which is the forming of esters, which is a carbonyl group, which is C double bond O, and then a carbon oxygen carbon bond. So the combination of those two things, turning an acid into an ester. And acetylations, it's similar to esterification, but it's only forming the acetyl group, which is the same as the acetate. And of course, polymerization, which is the form of long-chain hydrocarbons of various types. Now, these reactions are slow when left in nature by itself, and are dependent to a variety of conditions that are very hard to control. So making these guys in a lab is a little bit beyond the scope of what we normally do. So we just put them in a barrel and just let nature take its course. It's often hard to speed this up, so we often just don't bother. Now, there are some people who are trying, but it doesn't always work out. But all these are catalyzed by the wood extractives and the acids, and responsible for a lot of the color, the odor, and the flavor. Doing these reactions turns a bad liquor into a good liquor. Various 3-carbon, 4-carbon, and 5-carbon alcohols and acids, such as butyric acid, have unpleasant flavors or side effects, but you allow this reaction to happen, and voila. Butyric acid tastes like rot and smells like rotten butter. Ugh. You mix that with ethanol, you allow esterification, voila, you have pineapple flavor. Yet there was no pineapples anywhere in your whiskey. Amazing. Now, this diagram just shows the large range of ester flavors that are possible. Now, not all are possible in spirits, and not all are necessarily desired, but some of them, you have a lot of them. So by looking ethyl, 2-carbon with a 1-carbon methanoate, ethyl methanoate, you get like, if you have methyl methanoate, you have ethereal. You can have apples. If you have propyl, you can have like, looks like raspberries. You can just kind of fruity. You could have green. You could have peaches by benzyl methanoate. Woody, like a log. Citrusy, octyl, like grapefruit. But if you have methyl ethanoate, that tastes like glue stick. Or ethyl ethanoate, it's like super glue. You don't want that. But you go propyl, you have like pears. 2-methyl propyl, you have like cherries. So you could have jasmine, you have floral bouquet, but you could also have grassy here. You could have buttery, peachy. You may not want the buttery. You have vanilla with ethyl benzenoate. You could have balsamic vinegar. So you have leafy. You can have coconut down here, minty down here. Some wintergreen. You have a very strong blackberry flavor when you have butyl salicylic acid. So not all of these are, sorry, you can have some honey flavor, chocolatey flavored. So all these things, imagine you can have oily flavors if you have propyl decanoate. All these congeners that have been formed can then convert into various different esters that have a unique flavor profile. Thus, you get all these interesting flavors without all the necessity of mixing those fruits in at various times or another. This is brought about by catalysis. Now, one of the key things here is having a low pH, a large amount of protons there. pH is mainly controlled by the acetic acid, which once again, chief byproduct of toasting the barrels. Oftentimes it takes the 6 months or so before the pH becomes low enough for this to occur. But then once you do this, you can get some oxidation. The oxidation is a result of hydrogen peroxide. That tannins plus oxygen forms hydrogen peroxide and quinones. From there, we can undergo the what's called the Fenton reaction. The Fenton reaction, while the wood is being catalyzing the oxidation of ethanol and the congeners, it is also taming it and thus preventing the spoilage. That essentially we don't want this oxygen to get too rich. So we're forming the quinones and hydrogen peroxide in small, slow batches, we prevent over spoilage. So tannins are protecting us essentially, again, too heavily oxidized. Now, all these reactions are still relatively slow. Thus, a short aging time will result in an unfinished maturation that you're not really going to get the best out of. What we have here is what happens. Okay, so if I mix hydrogen peroxide in with alcohol, it produces the acetaldehyde. This acetaldehyde mixes with more alcohol. We can form, through a couple different steps, this acetaldehyde is a ethereal and faintly bruised green apple flavor. However, given enough time, enough reactions, you form diethyl acetal, which is described as delicate, light, and fragrant. This would be a top note in many mature spirits. So if you let it age for a little bit, you get the faintly bruised green apple flavor. If you let it mature for a long time, you're going to get the diethyl acetal. So it's all up to you. Do you want short time, quick turnaround, or do you want a much faster turnaround, a much slower turnaround, but a much better product? Now, of course, there's complexity layered on top of complexity. The flavor can be controlled by things like the starting components of our grain. What's in the grain? Types and effectiveness of the distillation. So it's not just like, oh, most whiskeys are like, oh, we take this much wheat, this much rye, this much barley. But if I mix those around, what's that going to do to the flavor profile? Different compounds. What type of distillation? So how many types of congeners are left? Is it filtered? What size of barrel? What species of trees were cut down? How were the barrels charred? What are the barrels previously used? How long are they aged? What were the relative weather and temperature conditions during this aging? What was the water source? All these make one whiskey slightly different from the next. These barrel reactions and extractions are all controlled by very complex equilibria with pH, the water to ethanol ratios. And certain reactions actually are favored under certain conditions. So you have different pH, this reaction is going to go with different pH, that reaction. You have more ethanol, this is going to be extracted. Less ethanol, that's going to be extracted. So you're going to have very, very complex, hard to reproduce things, reactions. Now, there are some people trying to accelerate aging because not everyone has the time to wait for 15 years. It's understandable why people want to just accelerate the aging process, because even making moonshine for production requires a very large startup cost, let alone producing enough product, barreling, storing it for multiple years prior to even be able to sell any product. And so how do you stay in the black enough that you can you have to plan several years in advance. So it's not just, unless you're making just moonshine, you plan several years in advance of like, oh, I'm going to make these barrels to be sold in 3 years time, and I'm going to keep making stuff every year so that 3 years time they can be sold, 3 years time they can be sold, and hopefully I'll make enough profit after the first set of 3 years that each year after that I can still be profitable and keep going. So there's various different methods, patents, technologies, and some are more successful than others. Now, some try to chemically reproduce the complex mixtures, which it's kind of like, doesn't quite feel right to just like say, oh, I'm going to mix in these congeners and hopefully they're the right combinations. It seems very sterile. But there's various different ones out there, like Cleveland whiskey. There's a company in there that use high pressure stainless steel tanks with various wooden staves. to essentially force the congeners to dissolve from the wood into the thing and speed up the maturation. Ranger Creek, they use much smaller barrels and harsher conditions to hopefully age it faster, using Texas heat rather than say like milder heat. So you go harsher cycles of it goes up, goes in, goes out, goes in. Smaller barrels means larger surface area per volume. High Spire, they use wine barrels with oak chips in them to try to make an interesting one. Jefferson's Bourbon, they use wave motion to increase the mixing. So they put their barrels on ships and allow the rocking of the ships to kind of stir the whiskey. Full Throttle Sloonshine, which is actually Tennessee again, they use the motion of the passing trains to mix the barrels. The vibrations, the trains barrel past because they literally put them right along the distilleries right along the railway, so it's passing trains to vibrate and help distill more, dissolve more congeners. And Spirit Works and Copper Kings and Tut Hill Town spirits, they all use a variety of acoustic sound waves to try to mix and catalyze this esterification. However, one of the most common ways to do this is use of staves or wood chips, and to try to force the ethanol-based extractions. They add extra wood to help dissolve more stuff. Lost Spirits Distillery has one of the most unique methods they have. They use tea bags containing wood chips, and they dip these like highly prepared tea bags for up to 5 minutes to simulate just 1 year of aging. This direct extraction from this tea bag simulates 1 year of aging. Then they use high intensity light to degrade the wood polymers within the wood chip and do that same process for 15 years, simulate 15 years of aging. That's essentially like high intensity light breaks down the wood so it can better dissolve. However, right now they can only simulate those 2 years. Increasing the reaction time, so more than 5 minutes, just to 6 days, increases the polymer concentration, but it doesn't help to speed up or slow down the aging. It's just more intense flavoring. Now, they're still working on trying to increase the evaporation of volatiles to simulate further aging, but they can pretty quickly produce the same flavor as 1 year aged and the same flavor as 15-year age with this method. But this only simulates various snapshots in the aging process. The idea here is like, as I said, the high intensity light breaks down the lignin that would naturally occur over a decade and a half of the heat cooling cycles. So you can only simulate those 2 years. They can't get 2 years. They can't get 5 years. They can only get 1 and 15. For some people, that might be enough. Now, it's not nice to fool your mother. Now, honestly, Lost Spirit rum came in second behind a 20-year rum. So obviously it's not bad. Not bad. So while this is not identical to barrel aging in terms of overall flavor profiles present, it still produces a pretty good product if it 1 second behind a 20-year aged rum. This is not exact science, though. We can't simply add chemicals and expect a good product. One patent suggested to add ethyl acetate because this is one of the most prominent esters that forms in the whiskey to help speed up aging. But Le Chatelier's may have something to say about this due to there's a very complex equilibria. A better solution may be just to increase the acetic acid concentration from that standpoint and then let it go from there. But small changes can have big effects down the line. Take, for example, the Lincoln County process for removing many of the heavier congeners that give you a headache. When you mellow it out, it may allow for a smoother drink right away, but for particularly longer aged whiskeys, this filtration will eventually hurt their flavors as it removes up to 30% of the congeners that would later turn into esters and thus contribute to the overall character. So, if you're not waiting long, mellowing out might be beneficial. But if you want to age it for a long time, it's not really worth it. So, in the end, it depends on what type of drink would you like to drink and what do you feel in the mood for? And here's all sources. Some of these are photo credits by me, actually having visited said distilleries. But some of these are from various Distiller Magazine posts, which has some very scientific articles in there. Some of these are various articles here and there.